back to another video. In this video, I'll be solving Gaussian integral. Now, you may have seen this online before as a very difficult integral to solve. Now, when you first tackle this integral, you might think, well, why don't I use a quick u substitution, where it's at u equal to negative x squared, then du by dx is going to be equal to negative 2x, but the thing is there's no x on this side, so we can't get rid of anything. You might think a integration by parts with the 1, but nothing ever comes of that. The only way that you can evaluate this is through a Taylor series or through this method, which I will teach you right now. So let's begin by thinking of what this function actually is. Now, this function is the Gaussian curve, aka the bell curve. So this models the probability of a given thing happening. So this is just the standard bell curve, normal distribution. So this value is so important to mathematicians because this helps us model so many functions in math. You'll notice the answer to this pops up in a lot of your probability equations and your statistics equations. So anyway, without further ado, let's begin to evaluate this. So first off, I'm going to multiply this integral by another integral, which is the same thing as itself. But we will be using y instead of our x. Now this is the same thing because we just have a function here. We could just say x is equal to, let's think of this, u. Then we just replug in our u's. It's still going to be the same value. Our u values are the same. So we know that these two integrals are the same. But the thing is, now since we're multiplying by itself, we now have to square this. Now, what we are going to do is combine these two integrals with Calc 3, which gives us that we can just multiply the inside of these two integrals because we will just be integrating them separate of each other almost. So this gives us e to the negative y squared, e to the negative x squared, dx dy, which then, by exponent rules, when you have x to the a times x to the b, that's equal to x to the a plus b. So this becomes e to the negative x squared plus y squared. So now we have that this is equal to our integral squared. So what can we do from here? Now when I see this, I'm thinking of a polar transformation. So let's set up our Jacobian for polar. So let's say that x is equal to r cosine theta and y is equal to r sine theta. Now when you switch from, let's say, a dx or Cartesian plane to a polar plane, you will need to undergo a coordinate transformation as well as multiplying the inside by a Jacobian, which is the stretch factor as you switch from one coordinate system to another. So for example, we are switching from rectangular to a polar coordinate system, and you will see that there's a value j in here, which is our Jacobian, which can be given by a very simple function in this case, which I will show you in a second, and then I won't do any explaining of it because it's pretty intuitive. But think of it like this: each square on your plane represents one of these. However, you can see it's really small down here, and as you go out further and further, it grows larger and larger, each one of these squares. So there's going to be a scaling factor which grows it larger by a constant quantity. So let's calculate our Jacobian. So we know that j is equal to the determinant of the matrix of our dx by dr, which is just going to be cosine theta, then our dx by d theta, which is going to be negative r sine theta, then our dy by dr, which is going to be sine theta, and then our dy by d theta, which is just going to be r cosine theta. So this is equal to these two multiplied, so this is r cos squared theta, minus these two multiplied, which actually becomes plus due to this negative sign, r sine squared theta, which is just equal to r. So our Jacobian, our stretch factor in this case, is just equal to r, which makes sense. because as you get further and further away from this, it increases with how far you are away. So the further away you are, the larger your square has been mapped onto that plane. So let's apply this transformation. So this lets us say that the integral from negative infinity to infinity, and then once again, negative infinity to infinity, of e to the negative x squared plus y squared dx dy is equal to our integral among new bounds, which I will talk about in a second, of e to the negative our x squared, but we need it in terms of this, so this is r squared cosine squared theta, plus our y squared, which is r squared sine squared theta, which you will recognize through this is just going to give us r squared. And now we have to multiply our Jacobian into this integral, so we have r times that. Now we have dr d theta. Now we are integrating over the entire xy plane in this case. So we want everything to be swept out by this hand of polar coordinates. So we will integrate from 0 to 2 pi radians to sweep out all of our values in that way through the polar sector. And then, since if you have a negative r, that is the same as your r multiplied by pi degrees, or switch over pi degrees, we can just integrate from 0 to r, or so from 0 to infinity for this function. Now this allows us to actually evaluate this integral, as now we can do a u sub, where u is equal to negative r squared, du by dr is equal to negative 2r. That gives us that our du divided by negative 2r is equal to our dr, so we could just plug that in right there, which gives us that this is equal to the integral from 0 to 2 pi, and then our integral through some bounds that we actually don't know right now because we're in a u sub and I don't feel like working that right now, so we'll just replug in later, of e to the u du d theta. This integral of e to the u from these two bounds just becomes our e to the u evaluated from our two bounds before, but I will replug in for our u's, our 0 and our infinity, and remember that there's a negative 1/2 on the outside here from our u substitution, of our e to the r negative r squared, which gives us that this is the integral. This becomes just negative 1 because this is 0 minus 1 over 1, which is just negative 1. So this just becomes 1/2 the integral of d theta from 0 to 2 pi, which just gives us that this integral is equal to 1/2 times 2 pi minus 0, so just 2 pi, cancels. So this integral is just equal to pi, and if you remember, this is just our original integral squared. So that means that the integral from negative infinity to infinity of e to the negative x squared dx all squared is equal to pi, which means that if we just take the square root of pi, that is equal to our initial integral. So we know now that the integral from negative infinity to infinity of e to the negative x squared dx is equal to the square root of pi. Not square root of x, the square root of pi. So anyway, I hope that you all enjoyed this video. I hope that you learned a lot, and thank you for watching. Please like and subscribe.